about that and if you have a container full of molecules at some temperature, then the velocity of the molecules doesn't all of the molecule doesn't move at the same velocity. They have a distribution, and in that distribution some of the molecules move faster than the others, some of the molecules move slower than the others. So there is, we can define an average. So that's why we define this RMS speed, which is root mean square velocity, and we also talked about average speed and etc. But just by providing the RMS speed or the average speed does not give you any information about the actual distribution of speed among the molecules, like how many molecules have this much speed or how many molecules have this much speed. They obey a law which is known as the Maxwell-Boltzmann distribution law. We'll see that today. So what we are going to do is distribution of molecular speed. Wait, people wants to join. Yeah. Like even if you start with an ideal system where all the molecules could start at the same speed, it's at same speed v0, no interval, nothing, all the molecule, you have n molecule are moving in the same speed. But after some time interval, they will collide with the walls of the container, they will collide with themselves, which will randomize the whole system and randomize the velocity in particular. So that's why it's important to learn about the velocity distribution or the speed distribution, how it is distributed among the molecules. And as I said, this distribution obey something called Maxwell-Boltzmann distribution law. So to start with, we'll define a probability distribution function, or let's say distribution function, which is f of v, that v denotes the speed of the molecule. So we define a distribution function. The function f of v which is called the distribution function. Now, assume that you have the container and you have a vessel or a container in which there are n molecules, and we want to know the distribution, velocity distribution, the speed distribution of that container. N molecule moving randomly, and if dn denotes the number of molecules which has speed in the range v and v plus dv. So dn is the number of molecule having speed. So you have total n number of molecules, they are moving in different speed. And dn is the number, if you chose, if you short all of them and you found that dn is the one, is the number, these are the number of molecules which have speed in this range. In the range v and v plus dv, where dv is also small and dn is also small. Then The distribution function f of v is defined as dn by n equals to f of v dv. Let's call this equation 1. This is how a distribution function is defined. So we can also say, in other words, that the probability that a randomly chosen molecule will have a speed in the range v and v plus dv is f of v dv, because dn by n is the probability of having that speed. So in other words, the probability that a randomly chosen molecule has a speed in the range v and v plus dv is f of v dv. This is the physical interpretation of the distribution function. So f of v is the probability per unit speed interval. See, f of v dv is the total probability, so f of v is the probability per unit speed interval. But here you should keep in mind that f of v is not the probability that a molecule has speed which is equal to v. So it's the f of v is the probability per unit speed interval where the speed is in the range v and v plus dv. So this one you should remember. You keep a note, cautionary note. F of v is not the probability that a molecule has speed which is equal to v. So this you remember in our notation. Now the probability is a number. So dn by n is a number which is equal to f of v dv. So f of v dv, it should be a dimensionless quantity. Now dv has a dimension of velocity, so f of v should have a dimension of reciprocal of velocity. That is the unit of f of v is, velocity is meter per second, it will be seconds per meter. Now with this preliminary steps, we are ready to do the derivation for the distribution. So to do the derivation for the how the distribution is and all about the molecular distribution, we have to assume something for our treatment. So we'll have some assumption just to make the calculation little bit simpler. First, you have to assume that there is no mass motion or a convection current into our system, into the in the vessel. The motion is completely random. Yeah, there is some questions or something. Okay, it's fine. You send it to Nirvana. That's okay. Okay, so what we are saying? Yeah, the assumption is that there is no mass movement of molecules. That is, there is no convection current as such. There is no convection current, and the motion is completely random. And second, you can assume the molecules like a point mass or a hard sphere so that they can only have translational motion. They do not possess any rotational and vibrational energies. So that makes it simpler in the calculation.
So why vibration is not possible there? Vibration energy is because
So
of
it is,
motion of particles, no, sir.
yeah, but in the treatment to make the calculation simple, we are assuming that there is no vibration and rotation. First, if we derive that, after that we can add the vibration and rotation as a, like, first we derive the f of b how it looks like, then we can add how it will affect if there is vibrational rotational motion. So initially in our treatment we assume that there is no vibration, then we go on to do the derivation, and then if there is vibration or something, then we can add that.
Okay, sir.
This is to just to make the calculation bit easier. Otherwise, it will complicate things and we'll lose the main point. We're doing it for the simplest case. Then we can make it complicated. They possess only translational motion. Okay. Now consider a volume element, which is like drawing it like a cube, just to preserve the rectangular symmetry, Cartesian scale, and this is your axis. Let's say, so you have your x, y, z axis. Let's say this is x axis, this is y axis, and this is z axis. So this is your origin. Now say the molecule is here, and its velocity is given by this v, velocity vector within that um, volume element. So and then the v, which is the velocity, it can be written as in terms of component. X component is vx, y component is vy, and z component is vz. And also the velocity square, it is v dot v, it will be vx square plus v square plus vz square. Now, having said that, If I say that we want to calculate the number of molecules which has speed and the range x component, where the x component is Vx and Vx plus dVx. So we are interested in the, if dnx, let's say, represents number of molecules having x component of speed in the range Vx and Vx plus dVx. Now we have defined the probability distribution function. Like here, the dn is the number of molecules having speed in the range Vx and V plus dV. So from here, we can write that dnx dnx over n, I'm taking the n on the other side, n f of Vx dVx. That means if I write it as like, so we can write this. So in terms of probability, so the probability, or you can talk about in terms of probability, that we have defined in both way. So if, here, the probability that a randomly chosen molecule have a speed in the range, this is f of v dv. And therefore we can say that a randomly chosen molecule, what is the probability that it has x component of velocity or x component of speed lies between Vx and V plus dV. So P1, let's say, is the probability that a molecule has x component of speed in the range Vx and Vx plus dV. X. So therefore P1 will be dnx by n according to our definition, and it is just f of Vx dVx. We call this 2. Similarly, if P2 is the probability that a molecule has a y component of speed in the range Vy and Vy plus dVy, it will be P2 equal to f Vy dVy. And similarly, P3, if it is the jet component, then we can say, we can write P3. So let's P2 and P3 are, similarly, we can write this, are the probabilities that a molecule has a speed in the range Vy and Vy plus dVy and Vz and Vz plus dVz respectively. Then P2 will be similarly to this. I will call this dNy. Right? The dNy is the number of molecules having speed in the range Vy and Vy plus dVz, and P2 is given by Vy f of Vy dVy, so 3, and P3 dNz n, where d and z is the number of molecules having speed in the range Vz and Vz plus dVz, and n is the total number of molecule within the vessel. It will be f of Vz dVz. 4. Now I ask a question that what is the probability that a randomly chosen molecule will have velocity component simultaneously in the range Vx and Vx plus dVx, Vy and Vy plus dVy, and Vz plus Vz plus dVz? That's the question I want to ask now. What is the probability that a randomly chosen molecule have speed in the range simultaneously Vx and Vx plus dVx, Vy and Vy plus dVy, and Vz and Vz plus dVz simultaneously in this three range, not individually. And from the theory of composite probability is the probability is the you have to multiply the individual probability. So it's P1 times P2 times P3. It is the product of individual probabilities. So that is this. It's P1 times P2 times P3. That's the answer. And I'm representing this as D3n. It's not cube, it's D3n by n, where D3n or XYZ suffix, where D3n denotes the number of molecules having velocity in the range Vx and Vx plus dVx, Vy and Vy plus dVx, and Vz plus dVz. Having speed simultaneously in the range Vz and Vz plus dVz. So if we multiply all the probabilities P1, P2, P3, here my P1 is f of Vx dVx, P2 is f of Vy dVy, P3 is f of Vz dVz. Then from this equation we can write D3n xyz is n times P1, P2, P3. F of Vx, f of Vy, f of Vz dVx, dVy, dVz, and I call this equation 5. Equation 5. Okay, where D3 n x y z is the number of molecules having speed in the range Vx and Vx plus dVx, Vy and Vy plus dVy, and Vz plus.
Sir,
Yes,
sir, why is it not n cube, sir?
n cube. This is just a notation. I just did it for
No,
D3
sir.
n x y z.
Where is equal to one n is there, no, sir? That n is found in all P1 and P2 and P3, no, sir. So when we are multiplying, why it not become n cube, sir?
I'm multiplying just the probability P1, P2, P3. So here the in P1, P2 you don't have n. Mathematically speaking, right? P2, P3
Oh,
you don't have n. P2 equals to FVY dVy. This is mathematics, plain mathematics, my friend. But physically, D3 is the number of molecules which has the speed in the range, in this range. And n is the total number of molecule. And D3 n by n is the probability of what we are discussing, right? It's not n cube, it's n. Okay, then we'll take a break of 4 or 5 minutes and then we'll start. Okay. Okay, I hope you are all have come back. Hello, am I audible?
Yes, sir.
Okay, we can
Yes,
now
sir.
now we can start our discussion. So now the trickiest part where Maxwell comes in, we have got the probability of the speed or the number of molecules which has the speed in this range. Then Maxwell's input we have to include here. And Maxwell said that we have to consider the fact that after a large number of collision, the distribution will be isotropic. That is, there is no preferred direction. Any direction is as good as any other. So you cannot say that the probability that the molecule will move more towards x-axis, y-axis, z-axis, and so on. So there is no preferred direction. It's isotropic. Therefore, the distribution function, which is f of v or f of vx or total distribution function, will be a function of velocity, not the component of the velocity. It should be a function of velocity. Now we have in terms of component of velocity. We have to convert them in terms of function of velocity. That is the total speed, not the separate velocity components. And Maxwell also argued that it must be such that f of vx, f of vy, f of vz is a function of velocity or a function of velocity square. Maxwell argued that since the distribution will be isotropic, it must follow f of vx, f of vy, f of vz, some function of velocity or some function of the modulus of the velocity, which is square root of v square. So j is another function. F is one function, j is another function. Now, for a fixed value of v, like if we fix velocity v, okay, I want to see in this how this velocity, where is that? Or let's say v you have from like 100 to 1000 meters per second. Now we want to say, okay, how much are the number of molecules which is having speed 600 meters per second? It's like that. So for a fixed v, then you can have the number and then you can bin it and to get the distribution. That's how it is done. So you have to consider a fixed v first. For a fixed value of v, your j v square will be a constant. That is how the function is defined by Maxwell. Hence, if you take a derivative of this function, it will be 0. So that is basically d of f of vx, f of vy, f of vz. D is the total derivative. It will be 0. Let's call this 6. Then you take the derivative using chain rule. So f prime dx denotes the derivative of f. So it will be df dv times dvx, and df dv is f prime. Other two will stay as it is. And then next the second one, plus the third one, this equals to 0. Now we divide the whole thing throughout f of vx, f of vy, and f of vz. Then we'll get something. Dividing throughout f of vx, f of vy, f of vz. And you can simplify it like you have f prime of vx, f of vx dvx, f prime of vy, f of vy dvy, plus f prime of vz, f of vz times dvz equals to 0. Let's call it 7. Now we have this equation, and also at the beginning we have written that v square equals to vx square plus vy square plus vz square. That's the modulus of velocity. And for a fixed v square is also constant. Therefore, from here also we can write twice v dvx, and I divide by 2 vy times dvz, vz times, this is dvy, this is dvz, equals to 0. So all the velocity has a constant equation, meaning if we can give me 2, then I can get the third one from this constant relation. Now we have to solve these two equations 7 and 8 simultaneously to get uh, f of vx, f of vy, f of vz. This is done using Lagrange's method of undetermined multipliers, and this is generally used to solve first order differential equation which has like variable coefficients. So I will not go into the detail, I will just tell you what to do. So you multiply equation 8 by constant multiply equation 8 by 2b. Why twice b? B is a constant that we can, that is, there is this rule of Lagrange's method of undetermined multipliers, but you don't need to do all that. When you will do mathematical physics 1, you will see, or when you do mathematics. So multiply 8 by 2b and add it to 7. To 7. By doing so, you will get this. You already had this. Now you have 2bbx from here, bbx like this. And similarly for y component, and similarly for z component, equals to 0. And this will be equation number 9. Now we choose B in a way such that the first one vanishes. In a way that this equals to 0. So we choose to find B in such a way. So you end up with the equation which has this part. Therefore, we will have this equals to 0. And now our velocity Vx and Vy and Vz, we said they are completely random and independent, but there is a constant equation where they are related with V square equals to Vx square, Vy, Vy square and Vz square. Out of these three variables, dVx, dVy, dVz can be considered independent. Let us take Vy and Vz to be independent, and then Vx can be found from this constant equation. And here, for a finite, in equation 11, for a finite dVy and finite dVz, the equation 11 will only hold if the coefficient, like which is in the square bracket, they vanishes separately. So we'll have this f prime Vy, f of Vy plus 2b Vy will be 0 to hold equation 11. And f prime Vz, f of Vz plus twice b Vz, this is also equals to 0. Now if you solve 10, 12 and 13, these are all first order differential equation, we will get f of Vx to be a is another constant, integration constant, Vx square, f of Vy, we will get at b Vy square, f of Vz, it will be a times e to the power minus v Vz square. This I call it 14, this one. So basically what you get, let's show you this. Let me show how it comes. So you had an equation like f of prime Vx, f of Vx plus 2b Vy equals to 0. It means you had d of f dv 1 of f plus 2b Vy equals to 0, something like this. This expression, oops, sorry. This expression is basically this d of dvx. This is x. Yeah. So from here, then we can, if you integrate, what you will get from this part is going to be this plus integration of 2b vx equals to 0. So this will give you log of v of x plus 2b x square by 2 plus some constant, integration constant. Let me take it as c to be some ln a. This is also constant. So you will have ln, take it as minus, let's say vx by a, then twice b vx square by 2, or from here, sorry, this is f of vx. But you do get the point. How to solve it? Running out of time. Do I have to continue this one, or you can you have understood how to solve it? F of vx by a. It's like that. Then you take e power on both sides. Then it becomes f of vx by a, where a goes to the other side, and e power b vx square. It's like that. Similarly, for the other two, then you can get this. So I think we should stop it here. So is that okay?
Okay, sir.
This is the first order differential equation, and you solve it like you just integrate it. This is a simple one. So you just integrate it and you get it. You arrange it such that where a is the integration constant and b is comes from the Lagrange's undetermined coefficient from there. So this is a and b in that form. Next day we'll carry it over from here. Is there any question?
No, sir.
Okay, then we'll stop it here, and we'll see you in the next week, next Tuesday, and we'll see how the distribution looks like, so on and so forth, and what we can, what are the stuff we can derive from this distribution. Okay, see you.
Thank you, sir.